Now talking about AMS simulations. So the current AMS SoC chip are more of top-down digital and bottom-up analog. So analog tools available in the industry provide less automation due to the complex nature of the analog design. So AMS simulation is more complex than either analog only or digital only simulations. So the general simulation technique followed is to verify the AMS block independently. So the interface part of the AMS block is treated as a digital, and the interface is verified after integrating with SoC. So what they are trying to say from this AMS simulation is, you take example of USB. In USB we have to perform AMS simulation when we are integrating UTMI and we are verifying. So during that time we have to use some analog layout, some analog tool like Spectre we have to use in order to integrate both digital and analog simulations. So since what problem they are telling, there is less automation available in the analog designs, so it is very complex to perform these type of simulations. So a general simulation technique followed to verify AMS independently. So basically how they are verifying the analog and mix, how they are performing analog and mixed signal simulation means they are verifying the block independently. Now the interface part of the AMS block is treated as digital, and the interface part, so that we will take that thing as a digital, and that interface is only integrated with the SoC, and we have to verify that thing. So coming to the static technologies, so till now we have seen simulation based verification, right? Simulation technology, in that we have seen event based simulators, then we have seen cycle based simulators, then we have seen transaction based verification, code coverage, hardware software co-verification, emulation, rapid prototyping, hardware acceleration, and at last we have seen that AMS simulation. Now coming to the static technologies, so static verification technology include lint checking and static timing verification. So you can say that what all the types of static technologies available, one is lint checking and one is static timing verification. So coming to the lint checking, so lint checking perform a static of the design code to verify syntactically correctness. So lint checking means what? So lint checking is a tool that will take your RTL as an input, and it will verify all the whether your RTL is syntactically correct or not. Then it will check any uninitialized variable, like at reset you have to initialize all the variables to some known state. Okay, so it will check whether you have initialized all the variable or not. Suppose unsupported construct, suppose you have used some unsupported construct like fork or join or initial begin and you have used, so in that case it will give you an error. Or you are having a port mismatches, suppose you want to connect a 6-bit port with another 6-bit port, but you are only using 5-bit and you are connecting, then in that case your lint checking tool will give you an error. So basically this lint checking is performed at RTL time, and it will identify some of the bugs which maybe not be possible to be discovered or uncovered with advanced tools. So lint checking will save a lot of time by finding simple errors in the design code. Now coming to static timing verification, so we know that latches as well as flip-flops, so these are some sequential element, right? So in order to so they are having some timing requirements, like sequential circuit has to meet the setup time and hold time, and they have to meet some they have to mimic some delays. Okay, so these timing verifications to determine the timing requirements we have to. So timing verification determine whether the timing requirements are being met or not. Okay, so the timing verification is a challenge for the complex design, since each input can have a multiple source, right? So that is a challenge. So that is what they are trying to say. So timing verification, then it's a very challenging job, that's why they are taking that thing as a separate type of verification. So basically the timing verification, that is static timing verification, is usually done by prime time and Perl. So prime time is from Synopsys and Perl is from Cadence. Coming to formal technologies, in design verification it is often very necessary, very difficult to detect bug that depend upon the specific sequence of events. So these bugs can have a serious impact on the design cycle when they are not detected early in the verification phase. So what they are trying to say means, we know that we can't say that our design is not having a bug. So we can found a bug if we are forcing some specific scenarios, and or if we are forcing some sequence of events. So then only we can find the bug. Okay, so basically we have to find the bug as early as possible before we should give that thing to Foundry. We have to find all sort of bugs. Okay, so detecting obscure bugs early on and exhaustively nature of formal verification. So every bug, so your formal verification tool will find those bugs. So it will find those bugs very exhaustively by forcing all sort of inputs. So actually formal verification methodology do not require any test bench. Okay, no need for any test bench like we are using in simulation based technology. We have to mimic one test bench. Formal verification methodology is simply tool specific. You have to give your RTL code as an input with some constructs and some you can say that assertions. Okay, so that your formal verification tool will take that thing as an input and explore each and every corner of your design. But theoretically one thing is very clear, that formal verification tool will not work for highly complex designs. So for block level verification, this is a good tool available in the market. See, they are telling that they are assuring 100% coverage. Okay, so there are three type of formal verification methods available. When suppose you are doing, you can say that you are performing formal verification, means you have to specify whether you are going with theorem proving technique, or whether you are going with formal model checking or formal equivalence checking. Okay, so we'll see one by one what are those techniques available. Okay, so first we'll start with the theorem proving technique. Okay, so the theorem proving technique is still under academic research. So still this theorem proving technique is under academic research, and they have not. So theorem coming to theorem proving, so this is still under academic research. Okay, so this technique shows that design meet functional requirement by allowing the user to construct a proof of a design behavior using theorem.